So let's have a look at an application of this idea of work to rocket science, rocketry as I'm saying here. In fact, it's a fairly simple idea. We're going to simplify even more to a very large extent, to the extent where you might think it's a little bit too unrealistic. But this is again just the first step for you towards, if you're interested in this kind of things, towards analyzing more and more about things having to do with rocket science. So let's see, what's the situation? Let's say that we're here and NASA has a rocket ready for you in Florida. Okay, so what we do is we take this rocket and we light it up, and the rocket starts blasting out and eventually gets into orbit. Well, that requires a little bit of work, doesn't it? In fact, if you have, I'm sure you have seen launches of the space shuttle or other rockets, you know that there is an awful lot of racket going on with all those engines going full blast and so on. There is a lot of energy expended, and so there is a lot of work. Because, of course, the object, namely the rocket itself, is going to be moved quite a bit. In fact, all the way out of the surface of the Earth into some kind of orbit. Okay, so what's the problem here? Why can't we simply multiply the force times the distance and be done with it? Well, because now we're in a situation where the object is being moved far enough from the surface of the Earth that the force that is needed, which of course is going to be related to gravity, is going to change. And here we need a little bit of background again from physics. The problem here is that in order to move that object, we have to take into account its weight. That's what's generating the inertia that we need to overcome in order to move this object. All right, the mass of the object is not changing. Well, that's not quite true, right? I mean, there is fuel being burned and so on, but for now we're just going to focus on how much work is being done on, let's say, the satellite itself or the capsule which is on top of the missile. Okay, so we're not going to worry about the work being done on the whole missile, the whole rocket, just on the top part, the part that needs to be deployed. Now, the weight of that part is going to change with height. How does it change? Well, we're going to use Newton's law of gravitation, which says that the force of gravity is going to be proportional to, according to some proportionality constant g, which is actually constant throughout the universe, but its constant is proportional to the mass of the Earth and the mass of the object that we're lifting, and inversely proportional to the square of the distance. Okay. Now, a couple of things to notice here. First of all, notice that in our application, g is constant. Well, it always is. The mass of the Earth is constant, and the mass of the satellite is also constant. Once again, we're ignoring the mass of the fuel and everything else. We're just working, considering the work done on the satellite itself. So all of that can be actually collapsed into a single constant divided by x squared. Not only that, but we need to remember that here x is not the distance from the satellite to the surface of the Earth, but according to Newton's law is going to be equal to the distance between the satellite and the center of the Earth, the two barycenters of the two objects. The satellite is small enough that it doesn't create a problem, but for the Earth we have to remember that we have to go all the way down to the center of the Earth. So let's keep that in mind when we set up our integral. Alright, so this force is changing because the distance is changing, right? So what we're going to do is, again, we're going to use our four-step process. So, step number one, we're going to slice this thing. What does it mean? It means that we're going to use, we're going to look at this vertical path that the rocket is taking. Oh, yes, by the way, we are assuming that the rocket is going straight up. I know that's not realistic, but we're doing that just to simplify things for now. If you feel like that, you may want to make the trajectory a little bit more realistic and see how that changes things. But anyway, we're going to slice it up. We're going to consider one of these slices, so this little tiny segment, okay? And we're going to call it, as usual, delta x. It's just a little piece of the motion or the distance that the satellite is covering. All right, now, at this stage, what we're thinking is, well, this delta x is small enough that we can assume that the force of gravity at that height is actually constant. And so what we're going to say is that the work done to move the satellite through that little slice delta x is going to be equal to F, which is our force of gravity at that height, times delta x, which is the distance by which we're moving it. So in this situation, F is going to be equal to k over x squared multiplied by delta x. So far, so good. Now we need to go to the last two steps. First of all, we're going to add up all the slices that we have to move the satellite through, and so the total work is going to be made up of pieces, each of them looking like k over x squared times delta x. So we add them all up, and then you will not be surprised to realize that the last step is going to be to take the limit. So we're going to take the limit as n goes to infinity of this sum. So we're taking more and more of these slices, which are thinner and thinner, so our approximation becomes an equality, and lo and behold, once again we end up with an integral. Again, we're not computing anything geometric, we're computing a physics quantity, but the structure is still the same. Limit as n goes to infinity of the sum from 1 to n of some function of x times delta x. That by definition is going to be the integral of k over x squared times dx. Watch out for the limits. Remember what I said was that we have to consider that the distance is the distance between the two barycenters. For the satellite, that's not an issue, but for the Earth it is. So our integral is going to be the integral from a distance equal to the radius of the Earth, or at least the radius from the starting position. Cape Canaveral is actually at sea level, so we can assume it's the radius of the Earth. And then the upper limit is going to be whatever the radius of the Earth is, plus whatever height we want to send the satellite to. Again, notice that this formula is fairly easy. The integral is also very easy to do, and we're going to do again some examples in class, and we're going to see how that works out in general. But from here on, basically there's nothing very exciting. All you need to do is compute that integral, and that's pretty boring at this point, isn't it? Or it should feel like that, right? Alright, so these are two applications. Can we apply the same four-step technique in other cases? You bet. Yes, there is all kinds of other applications. In fact, there are too many applications to count. Where there is we would have to do an awful lot of physical and mental work to go through all of them. So what we're going to do is, once again, we're going to see in class some other applications. Hopefully you're going to see on your own yet some more, and explore them on your own and practice on this four-step procedure, because in fact all of these applications will use this four-step procedure. So the trick is always analyzing the situation, slicing it up, approximating each slice, adding them up, and taking the limit. And if that is done properly, you'll come up with an integral, and hopefully that integral will not be too complicated to compute. Again, make sure that the details are done properly. As I said, if everything is done properly, then the integral will work, but if you make some mistakes in it, then of course it will not. So I'll leave that to you, to your experience. And by the way, yes, I do expect you to be able to practice enough to be able to handle any test questions, but probably this is a job in terms of figuring out how to apply integrals in these more general situations that is going to take for the next several years. And so keep working at it. Don't get frustrated, and just explore and get excited about all the applications that this single technique can provide.